everyone, we are Group 18. My name is Fahad Sindi and my colleagues are
Emmanuel Jose, Peter Curry,
Isaac Samuel,
We are here to present our project, which is Celestial Auto Tracker, and this might interest newcomers to astronomy, which they might have little background of the engineering and physics and math that goes behind it. Our project can track any celestial object that such as stars, planets, etc. And there are products there in the market, but for us, we try to make it as cheap as possible for these people who try to do it as a hobby or to go to the astronomy field. And we're gonna walk y'all through it and how we made it and the process, how it works through the PowerPoint presentation, and Peter's gonna go do the opening.
Yeah, equatorial tracking mount is a common type of mount which is used by astrophotography. For equatorial tracking mount, so once the alignment is done, the rotational axis will point towards the north magnetic direction. So the user can easily counteract the Earth rotation. So our celestial auto tracker will do all of these functions automatically with 3 different motors, which 3 different motors are controlled by microcontroller. So for polar alignment, we have to be like rotational. The axis should be equal to the rotation of Earth axis. So for that, the tracking axis points towards the north magnetic direction, and the angle tilt equal to the latitude where the mount is located. Our product will do all these functions, and after alignment, the rotational axis will rotate at the speed of Earth, but it will in the opposite direction.
The targeted market for our project is people who enjoy astrophotography and people who like to get a compact and a lightweight tracker, also in an economical and cheaper way.
Right, these are the benefits of a celestial tracker. The first thing is it can automatically track and align. The second thing will be the cost. We actually brought down the cost pretty cheap compared to our competitors. Another thing will be its assembly. It's super easy to set up, and we actually added the counterweight to reduce the torque and just make sure the tracking goes right. We actually added a manual alignment option to make sure if by somehow with the GPS something happening to the GPS or magnetometer going wrong because of any magnetic interference, we can actually manually align and then do the automatic tracking. Also, we have both battery, and we can actually power it using battery and external power adapter.
For the manual tracker, it needs a lot of stuff to make it perfect tracking. For example, the tracker has to be faced to the polar axis, and the polar axis has to be visually clear, and you need a aligned finder scope for the manual tracking. Also, it is kind of hard for the people that use manual tracking. They had to know a lot of stuff. Also, it will take a lot of long exposure that can cause a lot of noise on the picture.
Okay, for the automatic mount, the main objective of having an automatic mount is to do the alignment. That's where the most of the errors happen. So in order to do that, we add GPS and magnetometer to it, which can actually align properly, which saves a lot of time and errors. So our tracker works both in hemisphere. Like our tracker can actually do the polar alignment from the southern hemisphere where the Polaris is not visible. So our tracker can actually work without any user interface and ability to take long exposure photo, which is really hard in doing in a manual mount. So these are 2 images of Andromeda Galaxy. The first one was taken without tracking, and second one with tracking. As you can see, due to the Earth's rotational speed, exposure time is so limited in the tracking with the manual option.
So the maximum exposure duration was 4 seconds, and you need without any significant blur. to get a brighter picture, the ISO of the camera has to be increased, and it's gonna cause a lot of noise in the picture that I can see in the left side of it.
Yeah, but in case of the second picture, it's taken with the auto tracker. When it's taken with the auto tracker, the duration is like 10 minutes. So if you want to take like a picture for 10 minutes, we definitely want to use the auto tracker. So our product can easily do that. So some of the galaxies are so far. If you want to take a picture of a galaxy, if you take it manually, the picture will be like the first one. If we use this one, it will be perfect. And depending upon how far is the object, the dispersion duration will always increase. So this will be a perfect choice.
Okay, here is the concept of our project, and we actually have 3 motors connected to the project. And in the back here, we have motor number 3 and number 1 and 2 are actually inside the box. Motor number 3 performs the tracking and has a gear ratio of 100:1. And there is a gear attached to it to help rotate the tracking axis with the use of worm gear assembly to further increase the gear ratio. And we need this high gear ratio to achieve extreme slow rotational speed to match it with the earth speed. And for the other 2 motors, we didn't need this high precision, so we went with the 27:1 gear ratio. And motor number 1 here in the back, I don't want to break it. And motor number 1 here in the back, it does the elevation, and number 2, it does the direction alignment. Also, like you can see here, there's the magnetometer, which helps us with direction to help point the axis to the north direction. And this is the GPS, which gives us the latitude information to help us use that information to do the polar alignment. And also we have the inside the there is a gyroscope that helps us to do the elevation alignment.
All right, this is one of the most important calculations we have done for this, because the tracking is the most important part here, right? So for tracking, it has to match with Earth's rotation speed. Earth's rotation speed is 0.00418 degree per second, and we had to match our motor with that speed. So the stepper motor we had, it had a 0.018 degree step size, and we assumed the step size, the step to be taken to be 10, and we calculated it, and we got a 43 minimum gear ratio. And the tooth worm we chose was a 40, and we could have just kind of program it in a way it matches with the motor. Okay, so using those ratios, we calculated our motor speed, and it's 2.8 RPM.
So setting up the solar track is pretty much simple. It's a 3-part device. It comes with a tripod, tracking mount, and a mounting plate. First thing you gotta do is you make sure you have a clear ground level. Once you've done that, you can attach the base plate on top of the tripod. After attaching that, you have to carefully place the camera on the mounting plate, which is right here. After doing that, you have to attach this mounting plate to the pivoting base right here to do it. So there's a small video of the demonstration setup and application.
All right, I'm going to show you guys a video of how the automatic alignment and tracking works. All right, first you just plug in the external power adapter and turn on the device. So right now you can, I'm not sure if you can see it, but there will be a light blinking right here. Okay, there you go. Which means the GPS is trying to get the reading for the location. And whenever it gets to the location, the light will stop blinking and it will be solid. And that means we are ready for the alignment part. All right, so right now we are ready for alignment, and the first alignment will be the elevation. So you just click the switch, and the elevation alignment will start. After elevation alignment will be done, the direction alignment will start automatically. That's the direction alignment. And when both alignments are done, the light will turn off and you can start tracking by pressing the switch in the middle.
So here is a flow.
Okay. So I know it's a programming, but if the GPS works based on the location, right? If something happens, we should be able to do the tracking and do the alignment. That's why we added manual controls. So manual controls is pretty easy. You just press the red switch. It's an interrupt button. And it will start manual mode. And the first will be the elevation alignment. And you can use the left and right switch to move it up and down. Whenever you're aligned, you can start direction alignment and just press the red switch again and do press the left and right switch to move it left and right. And to start tracking, you press the red switch again and just press the tracking switch, which is the one in the middle. So whenever you want to stop tracking, you can just press the red button again.
So this is the flowchart for the programming, how we work with the microcontroller. First we have to turn on the red button, so the microcontroller wait for the GPS to get the signal. Once the microcontroller get the signal, the first thing is the elevation alignment. Once the elevation alignment is done, next is the directional alignment. So once both is done, it will be towards the north magnetic direction. And the microcontroller will wait for the user to press a button, the middle button, to start tracking. So this is what's happening in the program side.
So the competitors, we have two major competitors. The first one is Ioptron EQ30, and this one costs $1,300, and the other competitor, Celestron Advanced Auto Tracker, it costs $900. These both competitors have same features as the Celeste Auto Tracker. So it's the cost for making this prototype bracket. It costs us $664, and in order to do a bulk order like 1,000 of them, it's going to cost, for making one, it's going to cost us around $280.
All right, to conclude, automatic tracking mounts help you automatically align and track any cell-scale object. It has really good battery life. The battery itself will run for 2 hours. It's less maintenance, it's easy setup and easy to transport. And even the cost, we actually brought it, compared to our competitors, it's super cheap. Throughout this project, we were trying to prove that you can actually build a automatic strike tracking, and we achieved it. And we were trying to make it in a cheap way, and the total cost, if we are making like thousands of them, it will be around $280.
On the behalf of our team, we just want to thank Dr. Garcia for working with us from the beginning of the semester, with every step, with every calculation, with every piece of paper. He did a huge favor for us, and we just want to make him proud of us. And also we want to give credit to Rishi, who helped us with the coding. And thank you for your valuable time, and we are ready for your questions.
Thank you.
Any questions so far? So aside from reduced cost, what's the advantage or what's different about your system than what's on the market currently?
Well, we were focused on the cost first, because when we looked at the competitors, for even us, we were trying to buy one, and the price came out around $1,300, $300, and we were actually planning to make one long time ago, but it didn't come through. But when the senior pro came up, we were like, okay, let's try making it and let's see how much it costs, and it pretty much was super cheap to make it.
I see. And you're tracking the North Star, correct?
Yes.
Are you able to select other items? Like, do you have, because you're running off of Mega, right? So I don't know if you cascaded a set of stars, but are you able to select a star that you want to follow or something like that?
So it's all run with the programming, right? So there's a big library that of where the stars are located in every single step, because all the locations are updating every single second. So if we insert like the programming side to the microcontroller, we can do that.
But in between that, for ours, we try to, just like I said, try to make it cheaper, right? The competitors.
Guys, one thing. If you guys say cheaper one more time, you guys will be the.
Okay. No more cheaper. All right. So. Okay, I'm gonna try a different word.
Yeah, but
Exactly.
The other advantage is like it's like an open it's an open source, and you can track like not like the other ones where you are limited to their own library. This like it's an open source, you can track whatever you want.
Okay, so I got to see your presentation the first time around. Much better. Much better. You applied more to the audience, so that was, I definitely saw what you were doing. Comparison was much better. I didn't see too much of the comparison of the more expensive products. I saw the non-tracking and the tracking. How is yours comparing with the more expensive? Is the quality just the same? Is the exposure just as long? You said 4 seconds to take your image versus non-tracking.
No, it's actually, we were talking about the Faucet, that's with the manual tracking.
Okay,
So other picture was the automatic tracking, that's with the clear picture.
okay.
And your question was,
Well, you
The-
did a
your
comparison of the
combination, yeah.
non-tracking versus the tracking, and I was.
but the non-tracking one, it's really hard to do, like, everything is manual in there. So
Mhm.
every single time when the earth moves, you
Mhm.
gotta like go backwards like in a slower speed.
Right.
Instead of doing that, we use this tracker, the
Mhm.
stepper motor, like 100:1 motor is being used at a speed, so it can go to the earth speed backwards. So you can actually get a good image of it rather than holding it all the time.
Right, and just sitting and adjusting.
Yeah, like
Yeah.
if you see in the picture,
Right.
there's a lot of noise in the first picture.
Right, yeah, I saw it.
Yeah, and the other one with the help of tracking, power tracking, they can.
Definitely clearing out all
But
the.
is that other
stuff.
picture yours?
The
The-
first picture is taken by me, but the second picture is from the internet. Okay.
So that's not a picture from this product? You
No.
No.
The first picture is taken with my camera, but it's
Okay.
just a manual, like
Right.
yeah. If you want to take like the second picture was 10 minutes duration, right?
Oh,
So we
okay.
have to open
10
the
minute
lens
break.
for 10 minutes.
Okay.
If we hold it like this for 10 minutes, it's gonna move because
Right.
our earth is moving. So we have to move it like that, right?
Right.
So if you have a tracker, it will rotate automatically towards the earth. So it will stay the constant place. So we don't want to move with our hands. So
Right, because you're gonna,
Yeah.
create your own little vibration and stuff, so, yeah, no, I just, but the second picture is with the tracker?
Yeah, yes.
Okay, I think that's what it was. That's your picture, both of them.
Okay.
So, that's good. Anybody else?
What is from the 3 point of rotations that you guys have, which one is the most difficult to achieve? And what is governing that rotation?
Okay, well, all three would be pretty important, because for me, I would say that it's the elevation, because the force is acting on it. That's the only one with the force on top of it. All three doesn't really have much effect on it. And the tracking itself, you have to maintain that speed, 2.8 RPM with Earth's rotation speed. If it goes above or below that, then there's no point in tracking it.
I have a question on your tolerance. You guys went with you figured it out that you needed a 43 tooth gear, right?
Mhm.
But you went with the standard one at 40, right?
Yeah.
And the next standard one would have been what? The one above it, as far as like 40, I don't know. 44, 45? What's the next gear available?
So it was really hard to find a gear because with the exact gear ratio, so we find a easier, the delivery time, and it's perfect. We feel like it's perfect, so it's.
Yeah, we didn't need a very high gear ratio for the other two, but for motor number 3, we needed a higher one to match the rotational speed.
So what was
But-
your tolerance on that gear? As far as, so you cannot.
There was
exceed-
few of them. There were 48, and there was 36 one. So we kind of picked the closest one, the one we found from the calculation.
But did you find in your design what your tolerance would be on that gear? As far as what you could not
Tolerance?
exceed?
No, I don't think we have.
That's fine.
Well, first, the statement, like Liz was saying, the presentation was really good with the video. And on the first one, you were trying to show it in real time, so it was hard to see the image as it actually moved pretty slow. So I was really appreciative of the video. The question I have is, the camera that goes on there, is that compatible with any other camera, any digital camera that you have, is as long as it has the connection at the bottom?
Yeah, it's universal.
Okay, and the second question I have is that bar that's hanging out to the side, what's the purpose of that bar?
That's the counterweight.
The counterweight? Okay,
Yeah,
perfect.
right now it's kind of, the counterweight is fine, because
Okay.
the door itself counterweight the camera.
Gotcha, that
But
makes
if you're
sense.
going for anything more
Bigger,
heavier, you just add the
Like a
counterweight
heavier
and try to match it.
telescope, you need a bigger
Okay,
counterweight.
so if I, depending on the weight of the camera, I would slide it in and out?
Yes.
something like that? Okay, perfect. Thanks.
If you want to take a picture in an open space, non-protected location, with high winds that night, you have that opportunity just one every 10 years, and there's too much wind. Do you think that this thing will have the precision of anything that will have too much vibration? What would
It
you
certainly depends on the wind speed, right? I mean, even a hurricane can collapse a building.
No, no.
So, I'm just saying, it will totally come, I know it will be a 10-year thing, but if the wind is too fast, or it's gonna be, the tracking is gonna be.
Yeah,
Because
to be honest, we
it will hit on
didn't
the surface.
test it for that, but that's a good point for further improvement that we tested on
And
harsh
the
environment.
tracking axis itself, it's pretty small, so even if the wind is hitting it, if the bigger the stuff is, the more wind impact gonna be in that, right? And that axis right there, it's pretty light, so I'm pretty sure the wind will go across.
I'll say as long as it's stationary, or this is like on the tripod. If you get like a steady base plate, you might be an easier way to.
And the weight also, the whole thing weight, that's 22 pounds plus 15 on the tripod. That's pretty heavy. I mean, not compared to others, it's almost the same. But 36 pounds, if it's there, and for a wind to move it, it needs quite a power.
Another thing is, if you are taking a picture at wind, it will be more noise. There is no make sense. Like if you take a picture, if it's too much windy, you do not get a better picture. So mostly people do not use it when it's windy.
Yeah, and as long as it's steady, as long as it's like Isaac said, it's on a solid ground, it's gonna do the job.
And also we made it for like a perfect day or perfect weather.
Anything else? Thank you, guys.